voltage drop calculations appear correct. To run 200 amps at 240 volts over 700 feet, a 3% voltage drop will require a 500 kcmil wire. Working with 500 kcmil conductors presents certain challenges. Here are some options to make the installation more manageable. Firstly, consider using a lugged junction box. Install an M3R junction box next to the outdoor panel. Terminate the 500 kcmil conductors within this junction box using appropriate lugs. From the junction box, use smaller conductors such as 2/0 to connect to the panel. Secondly, consider using a 400 amp panel. A 400 amp main breaker is typically rated to accept 500 kcmil conductors. Upgrading the outdoor panel to a 400 amp model can avoid potential issues related to breaker ratings and conductor compatibility. For the meter loop, using a 200 amp meter loop for a 200 amp service is generally acceptable. However, ensure that the conductors feeding the meter loop are sized appropriately based on the actual calculated load of the service, not just the breaker size. To potentially reduce costs, perform a neutral current calculation. If the calculated neutral current is significantly lower than the phase current, the neutral conductor size can be reduced according to the National Electrical Code. Creating a new service point from the meter loop to the outdoor panel using a 3-wire configuration is allowable. However, it is crucial that the neutral conductor is properly bonded to a ground rod at the outdoor panel to establish a solid grounding electrode system. While not strictly required for direct burial installations, using conduit for the underground portion of the feeder offers enhanced physical protection for the conductors. Conduit also simplifies future maintenance or conductor replacement if needed. If splicing is necessary at any point in the run, use only high-quality splicing connectors that are specifically designed and rated for the conductor size and the intended application. Ensure that all metallic components of the electrical system, including panels, enclosures, and conduit if used, are properly grounded according to code requirements. Finally, and very importantly, arrange for a qualified electrical inspector to review the complete installation. This inspection ensures compliance with all applicable codes and standards, and verifies the safety and integrity of the entire electrical system. Given the significant expense of using 500 kcmil conductors, explore alternative design options that may reduce material costs. This could include considering a smaller wire size combined with the use of a larger conduit for heat dissipation, or even investigating the feasibility of a different voltage configuration such as 480 volts. A higher voltage allows for a lower current for the same power, enabling the use of smaller conductors. However, this would also require different transformers and equipment, so a thorough cost-benefit analysis is necessary. To elaborate on voltage drop, it's essential to understand its impact and how to mitigate it effectively. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause lights to dim, motors to run inefficiently or overheat, and electronic equipment to malfunction. The National Electrical Code recommends limiting voltage drop to 3% for feeders and 5% overall, including both feeders and branch circuits. The formula for calculating voltage drop in a single-phase circuit is voltage drop equals 2 times the length of the conductor in feet times the current in amps times the impedance of the conductor in ohms per foot, all divided by 1000. The impedance value depends on the conductor material, size, and temperature. Using larger conductors reduces the resistance and therefore the voltage drop. Another factor is the load current. Higher current results in greater voltage drop. Reducing the load or dividing it among multiple circuits can help to minimize voltage drop. Shorter distances also reduce voltage drop. If possible, locate the panel closer to the load to minimize the conductor length. Power factor also influences voltage drop in alternating current circuits. Improving the power factor by using power factor correction capacitors can reduce the current drawn by inductive loads, thereby reducing voltage drop. Now let's delve deeper into the grounding and bonding requirements. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protective devices like circuit breakers to trap and clear the fault. Bonding connects all metal parts of the electrical system together to create an equipotential plane, minimizing the risk of electric shock. The grounding electrode system typically consists of a ground rod, ground ring, or metal water pipe that is in direct contact with the earth for at least 10 feet. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in the National Electrical Code Table 250.66. The neutral conductor must be bonded to the grounding electrode system at the service entrance. This connection provides a low impedance path for fault current. Equipment grounding conductors connect the metal enclosures of equipment and appliances back to the service panel. These conductors provide a path for fault current in case of a ground fault. Ground fault circuit interrupters, also known as GFCIs, are used to protect against ground faults. These devices detect small differences in current between the hot and neutral conductors and trip the circuit if a ground fault is detected. Arc fault circuit interrupters, or FSIs, are used to protect against arc faults. These devices detect dangerous arcing conditions and trip the circuit to prevent fires. For direct burial installations, use underground feeder, also known as UF cable, or conductors that are specifically listed for direct burial. These cables are designed to withstand the harsh conditions of direct burial, including moisture, temperature changes, and physical damage. The minimum burial depth for direct burial cables and conductors is specified in the National Electrical Code Table 300.5. Typically, it is 24 inches for residential applications. When running conductors underground, avoid sharp bends and protect the conductors from physical damage. Using a layer of sand or other suitable material above and below the conductors can provide additional protection. To elaborate on the neutral conductor sizing, the National Electrical Code Section 220.681 provides guidance on reducing the size of the neutral conductor. The neutral conductor only carries the unbalanced current between the phase conductors. If the load is balanced, the neutral current will be minimal. However, if there are significant nonlinear loads such as electronic equipment or LED lighting, the neutral current can be higher due to harmonic currents. In these cases, the neutral conductor may need to be sized larger than the phase conductors. When calculating the neutral load, you can typically reduce the portion of the load that consists of electric ranges, clothes dryers, and similar appliances as specified in the National Electrical Code. For dwelling units, you can apply a demand factor of 70% to the neutral load for ranges and dryers. However, the neutral conductor must never be smaller than the equipment grounding conductor. Remember that the National Electrical Code is updated every 3 years, so it's important to stay current with the latest requirement. Consult the National Electrical Code and local amendments for specific requirements in your area. It is always recommended to consult with a qualified electrical engineer or licensed electrician to ensure that the electrical system is designed and installed safely and in compliance with all applicable codes and standards. They can perform detailed calculations, select appropriate equipment, and ensure that the installation is properly grounded and protected. Also, consider the long-term reliability and maintainability of the electrical system. Using high-quality materials and proper installation techniques will help to ensure that the system will provide reliable service for many years to come. Provide adequate access for maintenance and repairs. Avoid burying splices or connections that may need to be accessed in the future. Label all circuits and equipment clearly and accurately. This will make it easier to troubleshoot problems and perform maintenance. Keep accurate records of the electrical system, including wiring diagrams, panel schedules, and equipment specifications. This information will be invaluable for future maintenance and repairs. By carefully considering all of these factors, you can design and install an electrical system that is safe, reliable, and cost-effective. Remember that safety is always the top priority. If you are not comfortable working with electricity, consult with a qualified electrical professional. Electricity can be dangerous, and improper installation or maintenance can lead to serious injury or even death. Furthermore, when using a lug junction box, ensure the lugs are properly torqued to the manufacturer's specifications. Over-tightening or under-tightening can lead to loose connections and potential overheating. Use a calibrated torque wrench to ensure accurate tightening. Regularly inspect the junction box and connections for signs of corrosion or damage. If any issues are found, repair them promptly. Also, consider the environmental conditions when selecting the NEMA rating of the junction box. A NEMA 3R enclosure provides protection against rain, sleet, and snow. However, if the junction box is located in a corrosive environment, a NEMA 4X enclosure may be necessary. When using a 400 amp panel, ensure that the panel has sufficient space for the conductors and breakers. Follow the manufacturer's instructions for installing the breakers and connecting the conductors. Verify that the panel is properly grounded and bonded according to code requirements. When sizing the conductors for the meter loop, consider the future load growth. It may be prudent to size the conductors slightly larger than the current load to accommodate future expansion. Obtain approval from the local utility company before making any changes to the meter loop or service entrance. The utility company may have specific requirements for the meter location, conductor size, and grounding. Regarding conduit selection, consider the type of soil and the presence of any corrosive substances. PVC conduit is suitable for most applications, but rigid metal conduit may be necessary in areas with highly corrosive soils. Ensure that the conduit is buried at the proper depth to protect it from physical damage. Use proper fittings and connectors to ensure a watertight seal. When splicing conductors, use only connectors that are listed for the conductor size and type. Follow the manufacturer's instructions for installing the connectors. Stagger the splices to minimize the size of the splice bundle. Protect the splices from moisture and corrosion. When selecting grounding electrodes, consider the soil resistivity. Lower soil resistivity results in better grounding performance. If the soil resistivity is high, you may need to install multiple ground rods or use a ground enhancing compound. Ensure that the grounding electrodes are accessible for inspection and testing. Regularly test the grounding system to verify its effectiveness. A ground resistance tester can be used to measure the resistance of the grounding electrode system. If the resistance is too high, take corrective action to improve the grounding. For example, adding a second ground rod at least 6 feet apart, bonded to the original. Always de-energize the circuit before working on any electrical equipment. Use appropriate personal protective equipment, such as safety glasses and gloves. Follow lockout-tagout procedures to prevent accidental re-energization of the circuit. Be aware of the potential hazards of working with electricity, such as electric shock and arc flash. Take precautions to minimize the risk of injury. If you are not comfortable working with electricity, consult with a qualified electrical professional. Electricity can be dangerous, and improper installation or maintenance can lead to serious injury or even death. Remember to maintain a safe working environment. Keep the work area clean and free of clutter. Use proper lighting to ensure adequate visibility. Be aware of your surroundings and avoid distractions. Work with a partner whenever possible. This can provide assistance in case of an emergency. Know the location of the nearest emergency medical facilities. Have a first aid kit readily available. Be prepared to respond to an electrical emergency. This includes knowing how to shut off the power and how to administer first aid. Also, document everything. Keep detailed records of all work performed. This includes the date, time, location, and description of the work. Include photos or videos if possible. This documentation will be valuable for future maintenance and repairs. Share this information with the owner and any other relevant parties. Finally, remember that the electrical system is a critical part of the home. Proper design, installation, and maintenance are essential for safety, reliability, and cost-effectiveness. Take the time to do it right.